A vessel of mass m moving directly at velocity v possesses the momentum mv. Turning requires applying a lateral hydrodynamic force F from the rudder. For an ideal body, the rudder deflects the water, generating a sideways force that is proportional to the water density, the flow speed, and the rudder area. The resulting angular acceleration alpha is equal to the force times distance over the rotational inertia of the hull. So with a large displacement, there will be a very large inertia and there will be a small alpha. Thus, even with instantaneous rudder deflection, the turn begins quite slowly. So the game's rudder shift time is ultimately an abstraction of the time for the rudder to mechanically reach angle, and the time required for the hull to meaningfully respond to the induced torque. An ideal self-propelled body accelerates according to acceleration is equal to the force of propulsion, take the force of drag over its mass, where hydrodynamic drag grows approximately with the square of the velocity. A large mass results in slow acceleration and very slow reduction of velocity when propulsion stops, unless a reversed thrust is applied. And while this can be seen to an extent, the game often compresses these time constraints because the real physical inertia would feel too slow for gameplay. When an object turns in water, the centripetal force requirement is equal to the mass times the velocity squared all over the radius. The rudder force must therefore provide this centripetal force. Thus, a higher speed dramatically increases the required turning force, and with limited rudder force, the minimum radius grows quickly with speed. The hull shape also generates hydrodynamic lift and drift. The bow may grip the water better than the stern, producing characteristic slide or outward drift, and long slender shapes resist angular acceleration more. Higher speed churns fluid, which increases wake height, increases turbulence, increases spray, and increases noise. But a lot of it is also abstracted for gameplay. When a projectile enters the water, the drag increases by factors of hundreds relative to the air, and the deceleration is rapid, because the acceleration is equal to this very scary looking equation. Projectile also destabilizes due to the asymmetric pressure. The only exceptionally steep angles allow it to travel any further meaningful distance underwater. So the idealized versions of Citadel hits underwater occur when the projectile impacts water near the target hull. It decelerates but stabilizes enough to maintain a roughly straight motion. It continues forward at a velocity and then strikes the lower hull at a favorable angle. This is a very special case because water severely limits velocity and shallow angles cause ricochet off the surface. Ricochet probability grows when impact angle approaches grazing incidence and the normal component of momentum is too small to overcome material strength. Something more about AA is an ideal timed burst or proximity triggered explosion of flak creates a spherical pressure wave and sends fragments outwards with a radial velocity determined by its explosive energy. The probability of damaging a plane is a function of fragment density versus the cross-section of the aircraft, but the game abstracts this into zones rather than simulating individual fragments, which would probably take up a lot of computer time. Similarly, the aircraft motion in a fluid is as follows. The lift is equal to this other very scary looking equation. Turning requires banking, banking requires roll. Roll rate depends on inertia around the longitudinal axis and available aileron-induced torque. Sustained turn rate depends on lift-to-weight ratios and induced drag. Game versions usually compress this or scale these dynamics once again for performance. Similarly, airframe survivability involves structural integrity against shock, damage tolerance of control surfaces, engine vulnerability, and fuel system flammability. The detection is interesting. It does depend on line of sight, however ignores any atmospheric scattering, object contrast with background, and sensor resolution. The visual horizon is constrained by the geometry that the distance is equal to approximately the square root of 2rh for observer height h and the world radius r, though in this case you could probably consider the world radius to be infinite since last time I checked each map is perfectly flat. Similarly, a smoke cloud is governed by turbulence in the air, particle sizes, convection with wind, and buoyancy. Similarly, only being undetected whilst inside the cloud rather than behind the cloud indicates the game's understanding of opacity, which depends on the particle concentration along the line of sight. The games treat this as a black and white fixed radius visibility blocker, which itself can always be defeated by hydroacoustics or radars. Hydroacoustics themselves propagate via pressure waves in the water, and its detection, depending on its signal to noise ratio, and attenuation depends on the frequency and thermoclines of the environment. Similarly, a radar emits electromagnetic pulses and receives reflected power, you'll know how a radar works. And the radar's range is governed by a 1 over r to the 4. While these are a lot more realistic than any other video game out there, the binary state of being detected and not detected, and also the lack of environmental factors, results in a certain level of abstraction at this scale. Ultimately, if you were to compare this to any other video game, there is some ridiculously complicated mechanics intended to emulate reality as close as possible, whilst maintaining the gameplay and the fun factor of a shooter video game. So while it's not entirely realistic, that's not really the point, is it? I think that's about it.